Hi, I'm Abby Badwell, and for my course project for 570, I worked on an analysis of mixed training methods to train a 3D pose estimation and 2D object detection model. The motivation for my course project comes from autonomous driving. Pose estimation and object detection are important in the realm of autonomous driving. I've personally had experience in an internship working on a deep neural network for pose estimation, and therefore had a desire to understand other works in this category. The reason I focused on mixed training in particular is because gathering data to train a rigorous network is very expensive, as well as labeling that data is even more expensive. Being able to use additional unlabeled data in addition to labeled data would be extremely beneficial in solving the problem of never having enough data to train off of. The paper I focused on was exploring intermediate representations for monocular vehicle pose estimation. Intermediate geometrical representations, also known as IGRs, are used in this paper to estimate an egocentric vehicle orientation. The IGRs are computed from the 3D labels in the KITTI dataset and require these ground truth labels. This paper also proposes a new loss function allowing training to be done with unlabeled and labeled images, which is essentially a mixed training strategy. However, it cannot entirely rely upon labeled data. And below are images of the ground truth data. The overall layout of this network contains two networks. The input goes through a heat map fully connected layer, which passes these heat maps to another fully connected layer to produce a 2D mapping. Using an affine transformation A, it creates a final 2D representation that gets passed through a lifter network, whose purpose is to lift the 2D representation up to a 3D representation. This is how they produce the final pose estimation. The code base of this paper features a plug-and-play feature, therefore you can use different networks for the heat map and fully connected layers. I will go over a quick overview of the mixed training with unlabeled data equation outlined in the paper. So psi of x uses tau of x to create a matrix representing the transformed points. Phi of x is the interpolated matrix transformed using the camera's intrinsic data, which is held in matrix K. And it does this such that it can implicitly encode instant location within or relative to the centroid. So L1 in this loss function represents the average heat map loss. L2 is the loss used to supervise the 2D networks. L3 respectively is the 3D networks. And L4 is used as a cross-ratio loss function such that unlabeled vehicle data can be used. I worked to understand how loss weights would change the accuracy of the model, as the loss functions used in this implementation are the backbone of a good model generalization. The first line in the table is the suggested weight in the paper for loss weights, and as you can see, it performed with 47% accuracy. I played around with a few different weights without the use of mixed training via unlabeled data. With the addition of unlabeled data, I was able to achieve a higher accuracy model of 55% on my computer. The cross ratio is mainly computed using the smooth L1 norm loss, and the 2D and 3D losses are computed using the L1 norm loss. The mean squared error is used for the heat map loss. As you can see, the added mix of unlabeled data increases the performance of the model. Overall, the accuracy was low due to the limitations of my machine. I was only able to train a single epoch with a smaller data set in a reasonable amount of time. For my reimplementation, I reimplemented the IGR extraction formula from the 3D labels given in the KITTI dataset. This formula was given in the paper. In the paper, it was suggested to use a 2x2 B matrix, and they specified values, which I used. In an attempt to increase B, I saw an increase in the overhead, which led me to understand why the authors of this paper chose a 2x2 matrix. The 3D labels provide 8 points to represent the 3D cuboid, and by interpolating these 8 points, we can create a 3D sparse matrix to represent the cuboid. This matrix will become less sparse with a larger B, and thus leading to better model generalization, but as I said previously, it would increase overhead, and this calculation would make longer training times. Some key takeaways from my project were that methods for pose estimation and object detection can be unsupervised and still compute with supervised models, which I learned from the other papers in my project. But ultimately, combining supervised and unsupervised models will lead to better generalization of a model to be used in an autonomous driving environment, since in an autonomous driving environment it is very important to be accurate. Also, the overhead of geometric computations made between these image features could lead to longer training times and the need for many GPU resources.